So welcome to our STAMPS webinar series. So we're very fortunate to have Dr. Jenni Evans here today. Evans is a professor in meteorology and atmospheric science at Penn State. Evans was trained as a mathematician. She earned her undergraduate and doctorate degrees in applied math at Monash University. She is the director of Penn State's Institute for Computational Data Sciences. And Evans was recently the centennial president of the American Meteorological Society. For over a decade, Evans was the lead meteorologist advising the Florida Commission on Hurricane Loss Projection Methodology. So Jenni Evans is a perfect speaker to have here for STAMPS because of both her research depth and width. Dr. Evans' research spans tropical cyclones from genesis to decay, extratropical transition or landfall, and the impacts of climate change on tropical cyclones. Evans uses a variety of new statistical methodologies, and the tools of her research include observational diagnostics, statistical analysis, and modeling observations, simulations, and reanalysis, and dynamic modeling. So today she will be talking about unscrambling ensemble simulations to improve hurricane forecasts. And with that, I'll let Jenni take it from here.
Thanks, Anne. And thanks for inviting me. So I thought I would tell you just a little about the Institute, since I'm not sure how many of you have heard about ICDS, and then the vast majority of the talk is on the research that was advertised in the abstract. So ICDS was originally called the Institute for Cyberscience. Last year, we changed the name. We are an interdisciplinary university-wide research institute at Penn State. So we answered to the Office of the Senior Vice President for Research. There are 4 other institutes like this at Penn State. And our mission is to build computational and data sciences research across the university system. So we do that in 3 ways. We first of all build the scholarly community. We both do that through a co-hiring tenure-line faculty with departments across the university. Currently, we have 34 co-hires across 22 departments in 8 colleges. We also develop or help to get going interdisciplinary research initiatives across a wide spectrum. AI and quantum are a couple at the moment, so is data science and diversity, so is predictive modeling, a few others. Broad in scope because researchers have many interests. And the third thing we do is we run and develop and orchestrate Penn State's high performance computing infrastructure. So with that
So Jenni, I think we're not seeing your video right now. You may have disabled it when you started to speak.
You mean of me or?
I think it's of yours. I see your slides, but
yeah, if you can with your camera, yeah, now we see it. Yeah, so
Oh.
your camera somehow went offline at some point, but now we see.
Oh, okay.
And can you see the slides as well?
Yes.
Okay, good.
Yeah.
All right. So I just wanted to touch on that briefly because ICDS has been growing rapidly, and we had a very small community about 3 or 4 years ago. So since you're just down the street, I would hate to think that you hadn't heard about us and learned about us and would more broadly want to reach out to us whenever we could help or collaborate in some way. So I'm here to talk about hurricanes, tropical cyclones, and improving understanding as well as forecasting. The motivation for this work is forecasting. We all know that they're damaging and terrifying, but I think so let me set this up and then I'll let it run. It's a short video. This is Severe tropical cyclone Ingrid making landfall in North Australia. At the time it was making landfall, Ingrid was about 130 or 140 mile an hour winds. It made landfall in a very sparsely populated area. You're standing on the veranda of the house where the Bureau of Meteorology forecasters lived, and they're filming the storm as it goes by. Look out for the pieces of flying roofing, among other things. So I'll just let this run quickly and give you a sense of what a hurricane landfall looks like.
Left.
So that's what a hurricane landfall looks like. And the thing that had never occurred to me is afterwards how quiet things are if you're not in a city. There's no birds and the vegetation is pretty damaged. So that's the kind of system I'm talking about today. Just for a bit of context, this is what the North Atlantic Basin has looked like this year in terms of tropical cyclones. There were 30 named storms, which is the most on record by 2 compared to 2005. 12 US landfalls, and seven of them being tropical storms. There were 4 major hurricanes in the last 2 months, October and November of the season. And I'm going to use 2 of those, Hurricanes Eta and Iota, that both made landfall in Nicaragua. They made landfall there 2 weeks apart. I just want to use those as an example of the kinds of challenges for the forecast that we're facing, and part of the motivation for doing the work that I'm going to talk about here today. So this is Hurricane Eta. You can see the complex track that Eta took, eventually crossing northern Florida after waltzing its way through the Caribbean. The colors, the cooler colors are weaker wind speeds, and the warmer colors are intense, with oranges being more than a category 3, and the red being cat 4 or 5. So more than 110 miles an hour at least. So this is Hurricane Eta. Eta made landfall on the 3rd of November in Nicaragua. And then Hurricane Iota, you can see much simpler track, but you can see that red and orange right as it's coming on shore in Nicaragua. And that made landfall. So this was the 3rd, this was the 17th. And I've shown you here the images of the 2 storms at peak intensity. We'll come back and look at them, but if you can see in Iota, it's even more symmetric perhaps than Eta. And you can see a pinhole eye in there. And that's very characteristic of a very intense tropical cyclone, the symmetry and the pinhole eye both. So here's Hurricane Iota. I just talked to you. So this is a visible channel. You can see the storm symmetry and its the eye structure. You can also see the spiral bands of convection that are moving out from the storm. So you can see an expansion in the area of rain associated with Iota. At this point, it's a Category 5 system. So Category 5 starts at nominally 157 miles an hour. And there is no Category 6, right? So these are the most intense and damaging storms. Iota weakened slightly as it made landfall. This is now Iota looking in the infrared colored infrared. And the reds are very high clouds, very heavy rain. The green is still a large area of rain. You can see the spin slow down. It's crossing the coast right here. So you can see the rotation slowing down, and you can see the red disappearing, but the large area of green. So that's implying that the winds are decaying, but the rain area is not reducing. And what is also happening, though, is that the storm is slowing down. So you can imagine you've had these very intense winds coming on shore, a lot of wind damage, and then the storm slows down and it just keeps flooding rain on this already damaged environment. And then, of course, Iota is coming ashore after Hurricane Eta. So the ground is already saturated. There's already been landslides, mudslides, and it's here we go again. So nominally, Iota was a Category 4. You'll notice that 2 mile an hour extra wind, and it would have been called a Category 5. So if I were in Nicaragua, I would feel justified in saying I'd had a Cat 5 landfall. So that's Iota. And so the main points here are the symmetry, the very high clouds, which is the red, the pinhole eye, which is a signature of the storm being at its most efficient at processing energy, and this large cloud shield represented by the green colors here, showing you the extent of the rainfall region. So that's Iota. Here's Eta near landfall. Now this is a closer view, so Eta isn't 5 times as big as Iota. But again, I wanted you to see now here the color code is that the black is the highest cloud tops. But you're seeing the same basic thing again, this very intense system. Here's the coastline. Eta's approaching. This is on the 3rd of November. And again, this large rainfall region. And again, I'll show you the track of Eta again later, but if you remember, Eta came onshore here and then turned and went out towards the Caribbean and eventually crossed the Florida coast or crossed the peninsula. So as it's coming ashore, again, Eta is slowing down in forward movement. So you've got this very broad area of heavy rain. Also, because it was going in a straight line, it's building up storm surge and wave action. So at the coast, you've got extreme winds, you've got storm surge, you've got rain, you've got wave action. As you come in, you've got the rain, you've got flooding, and then associated landslides and mudslides in areas where the topography, of topographic relief, if there's any instability in the soils. So there's many different issues here with what happens as this system's coming ashore. And these 2 storms came ashore within 25 kilometers of each other. So I'm going to take a little bit more of a look at Eta to demonstrate what I'm trying to do today. So thinking about what do we need to know if we're forecasting. So forecasting is ultimately a job of keeping people safe. All right. when we forecast the weather, it's great. Am I going to wear a jumper today? Am I going to take my umbrella? Am I going to get in the garden? But it's also, do I need to evacuate, or what kind of conditions will I be flying in, or all these other things, or even, that are much more critical than convenient. So when we're thinking about this kind of a forecast, we care about where's the storm going. The impacts aren't going to happen if the storm's not there. We're used to thinking about the intensity. So how bad are the winds going to be? And that's certainly important. Rainfall is something that is coming as a hurricane condition. Rainfall is being talked about more and more on the scale of the system. You've probably heard people talking about how systems now seem to be more efficient at processing rain so that we're getting heavier rainfall events. And as I just mentioned, and we'll probably come back to, the rainfall or the precipitation, rain or snow. Depending on the next few things, the rain can be even worse, right? So the structure, what region? I was talking about how these storms, the rain area was spreading out, and getting back to the track, spreading out, large area of rain, slow motion, much more rain, flood, landslides, and so on. So then you care about where the people are. So who's at risk and who is the forecast for? So that's what I'm thinking of. What I'm going to talk to you mainly about today is the track and forecasting the track. And I can talk, and then I'm going to do the clustering based on the track and just give you a sense of how that clustering discriminates between different evolutions of an example storm. So you can see how we can use the clustering to understand how the storm might evolve in different pathways, and then to use that to make a better forecast, and to use that to go back and understand the physics underlying that system, so that we can also just get a better handle on these systems and how they evolve and what we need to do to simulate them better. So this is an example of what the forecasters have to use. And in the early 2000s, this would have been a really good day at the office. So what I'm showing you here is what forecasters affectionately refer to as a squash spider. And I'll come back, you'll see that there are worse spiders coming up. But what that means is if I'm going to make a forecast and I look at where those storms are going, they're indicating everything from crossing Central America into the East Pacific, which happens on occasion, or making landfall in Belize, right? Or whatever. So there are many people who could be impacted in that area. So at this time, Hurricane Eta is just 35 miles an hour. So it's just a marginal tropical storm, nothing to write home about, but it's near land, so we care. All right, so now we're a day later and the storm is 75 miles an hour. So now it's a Category 1 hurricane, and you can see much closer to land. And again, that there's a real spread of the storm, of the model forecasts that we're seeing. Now, a day later, it's 150 miles an hour. So this is almost a Category 5 system, and that's in one day. So there's something else along with, so there's multiple things here. The storm became from a Category 1 to almost Category 5 in 24 hours. That means an enormous change in the structure of the storm and an enormous change in the expectation of the storm threat at landfall. So, and you can see that the crosshairs is where the storm is at that time. The storm is right on land, right? It's just making landfall now. Remember I said the 3rd of November was the date of the landfall for Hurricane Eta. So 150 miles an hour at landfall. All right, 24 hours later, it's back to 70 miles an hour. So it's still on shore. There's the crosshairs, and it's beginning to make the turn and move out towards the Gulf of Mexico. So many things there. It's a difficult forecast. And the models are showing it's difficult. It's difficult because the physics is rapidly evolving, even if it wasn't near land. And then the impact of land is also going to change how that system evolves. So Eta is a great example of a complex forecast. And what else do I want to say to you about that? Okay, so I want to just get into how we do the modeling and how we think about the modeling. National Hurricane Center, the US National Hurricane Center has been around since, oh gosh, well, it's been active since the 1920s in some form or another. This is looking at the numerical modeling on the right and the forecaster skill on the left. Since 1970 to 2019. So on the left, this is what, sorry about that. On the left is how the forecasters, the people, have done at forecasting the systems. So going from red, green is 48-hour forecasts, so 2-day lead time, and these model skills are all at the 2-day lead time. You can see blue now is 120-hour forecast, so 5-day lead time. And if you look at the 5-day lead time now, and you come across the skill at 5 days now is about what the skill was at 2 days in the late 1990s. So, you know, it's still 150-mile error, but that's a pretty impressive increase in skill among the forecasters. If you look over the same period, this is not a homogeneous selection of models, of course. The models back here pretty clearly were less sophisticated. And as our model skill improved, as our data improved, as our understanding improved, and as our computing resources improved, you can see this incredible both increase in skill and more of a convergence towards similar levels of skill. There's sort of devils in the details there because there's all kinds of incestuous links between the models. But nonetheless, we've had a dramatic improvement and the models have been a large part of the story, although not all of the story. So I'll just return to what we're doing and then I'll take the model story a bit further on. I should have reversed that. So this is what we're trying to predict. This is from Hurricane Eta. We're trying to predict the wind, the rain, the storm surge, the flooding, and the wave action so that people can be safe. We say to hide from the wind and run from the water. That's certainly in the US where we build for better than a Category 3 safety in terms of our structures. Clearly that's not going to hold up in a Cat 5, but you cannot hide from the water. You have to move out of the path of the water. And so that's very critical in the forecast. Right, so that's what we're trying to help people get away from. And the 48 hours is important because that's when we want people to be the latest time they should begin evacuating. They should be on the road and leaving by 48 hours if they're going to leave. All right, so I'm going to show you what we're doing in 2020 in terms of translating forecasts, numerical weather forecasts, into products for the human forecaster to hopefully improve upon. Maybe you wonder why a meteorologist should be running an Institute for Computational and Data Sciences. And I would say, well, that's just perfectly natural. If you look at the history of computing, when John von Neumann had this ENIAC system, he was actually looking for what can we use to challenge this computer. And he connected with Jules Charney at MIT, who was a young meteorology professor, and they decided that numerical weather prediction would be the ideal use for the computer. On the right here, I just thought this was fun. This is showing the processes that it took in order to make a forecast. And on the left, you can see computers, that is the women who programmed the system, and men. But so this was where we were in 1950. And so we created numerical models. And we would run our numerical model and it would tell us what the weather would be tomorrow or where the storm would be tomorrow. We would have one realization of the storm and we would use that and we would make a forecast. And that ended up not being ideal. And so in the early 2000s, we started to combine groups of these deterministic forecasts. And then we called that a multi-model ensemble. And that's what I was showing you up till now with the forecasts of Hurricane Eta. So that was an ensemble, a group of independent models that were all focused on forecasting the same event. So a positive about the multi-model ensemble is it gives you a sense of when it's a particularly difficult forecast, right? But the drawback still, even though you're getting those multiple realizations, the models are so different from each other and how they're run is very different. So the diversity among them could be in how the models operate themselves, in the data that was available to them on the day, or a number of other factors. And each model, as it turns out, has its own climate, if you like. So each model has a tendency to relax towards a particular subset of solutions. We're also not sure that that group of models is spanning all possible realizations of the future. And so while it's helpful and it does remind us that these things are imperfect, in and of itself, a multi-model ensemble is good, but not the final answer. So then probably only about a decade ago or so, we started running, or maybe a bit longer, we started running a single model many times. So for the 0600 initialization of, say, the hurricane WRF model, which is the weather research and forecasting, we would run that at incredibly high resolution with all of the data we had. That would be the deterministic forecast. And then we would run maybe half a dozen more that weren't such high resolution and so on. And that would be a single model ensemble. And so the single model ensemble is designed so that ideally it spans the space of all possible solutions to the initial conditions in that system. And so that is an improvement because the perturbations take into account the vagaries of the model, the issues with data quality and distribution, and the issues with the parameterization, and also more recently the actual physics, the actual storm. So if there's a hurricane there, your ensemble will look different to if you're worrying about a blizzard. So it will have different initial perturbations. So anyway, that's the progress. So what I'm going to do today is I'm going to look at a multi-model ensemble of single model ensembles. So we're going to look at an ensemble of ensembles. And so I'm taking 4 of the most skillful global model forecasts. So the European Centre has an ensemble of 51 members. The UK Meteorological Office has an ensemble of 24 members. The US Global Forecast System and the Canadian Meteorological Centre both have ensembles of 21 members. So that gives me a super ensemble, if you like, of 117 members. And from that 117 individual forecasts, my goal is to reduce that set to a single digit number. So, you know, less than 10, ideally many less than 10 actual scenarios. So now I'm going to get into what we're doing and show you some results. I just noticed the time. So here is a setup. This is Hurricane Sandy in 2012. Sandy is they called it Superstorm Sandy. Made landfall in New Jersey late at night on the 29th of October in 2012. You saw visions of New York City being flooded and all kinds of other issues. So we're going to take a set 8 different initial forecast times. We're going to look at 7-day forecasts. And we're going to look at that 117 member ensemble. So 117 member ensemble, 7-day forecasts every 12 hours for 4 days or whatever it is. The picture shows you in red what the storm actually did, and in black, the 117 members when the storm was down around Cuba. And so you can see again the spread. And so those are 7-day forecasts. So you can see, since a lot of them are getting far inland, that the storm is going to make landfall in less than 7 days, right? So what I want to do here is to take this set of forecasts and to develop a mixture model for some number of clusters to partition that into a small set of scenarios. So the method I'm using, and I haven't put references here, this work was done in collaboration with Francesca Chiaramonte and Prabhani. Gosh, Murali, you need to help me with her name. Anyway, Prabhani, both Penn State Statistics, and then a variety of colleagues at Penn State and at Karlsruhe, KIT in Germany. Anyway, so what I'm doing here, to create the mixture model, I have to select, all right, go back, take a look at those tracks. You can fairly easily convince yourself that a polynomial could be used to model the shape of those tracks. And so that's what we're going to do. So we're going to cluster along the track. Point clustering doesn't make any sense in this scenario. I care about the life cycle evolution. So I'm going to cluster along the entire life cycle. So I need to model the tracks so that I can define the shapes of the clusters and use that to partition this system. So what I'm doing is I'm selecting an order of polynomial and a number of clusters, and I'm going to select many combinations of these and then decide which ones I want to use. And then I'm using expectation maximization algorithm to iterate to determine the parameters for the models, for the model for each of the K clusters. And I get that solution, I get my parameters, I get my posterior probabilities, and then I do that 500 times so that I make sure that when I choose my solution that it's converging to a global maximum, not a local maximum. So that's maybe overkill, but we wanted to make sure that we did the best to get the right outcome. And then I have now the many solutions. I have the many combinations of polynomial order and number of clusters. So then I first of all select the best model for each combination, and then I decide which order of polynomial and which number of clusters is my preferred solution for clustering this whole system overall. And I have 3 metrics I'll talk about that I use to make that determination. So this is just simply we're modeling the tracks as some kind of a polynomial fit. So we need to, Q is the order of the polynomial we're going to be using. So we need to determine what is the best choice of Q. And K is the number of clusters that we're going to develop. So we need also to determine K. So we come in first of all and we say we'll assign those, and then we're going to get solutions for the regression coefficients beta and for the variance. So then we're going to use expectation maximization to solve to get the specific parameters for each of the mixture model, candidate mixture models. And if you think about it in this context, each of the clusters is really like a polynomial shaped pipe around a Gaussian distribution. So yeah, so this is how we get the individual model. Now, as I said, we want to make sure that we converge to a global maximum log likelihood. We maximize the log likelihood. So we do this 500 times. And then I will show you now, these are the diagnostics we're using to determine which models we ultimately select. So the Bayesian information criterion, the BIC, the more parameters and the more complexity you add to, if you're just using maximum log likelihood, MLL, you'll get a better metric, better value. But with the BIC, you're penalized for making things more complex. So you have a balance between complexity and satisfying the convergence criteria. So I like this since it sort of forces me to be thinking about a simpler solution that still does the job. So that's the BIC. The mean squared displacement. So what we're looking at here is the compactness of the cluster. So we're looking at the within cluster spread and also the frequency of outliers for the individual clusters. And so this is looking at displacement relative to the central track of the path cluster you're considering. And then the final one is the strength of cluster assignment. Since we've got probabilistic cluster assignment, we wanted to see whether or not we had a lot of ambiguity in the solution. It turns out that this isn't such a compelling metric because we do have very strong cluster assignments. So those are the 3 diagnostics I'm using for the cluster solutions I'm taking as candidates. In all cases, those 3 diagnostics, a lower value is superior. So we're going to look for lower values in all of them. So now I'm going to turn and use Hurricane Sandy as an example. And these are images just to show you the sorts of things that hurricane can do in West Virginia, New York, and New Jersey. So on the left top, that's a blizzard that hit West Virginia, directly related to Sandy. In the bottom in the middle, you can see what wind damage, those roof pieces of roof projectiles, what they can do to a building. This house had a combination of wind and then fire after the wind, and you can see, of course, flooding and tree damage and the consequences. So that was the impact of Hurricane Sandy. Again, this is the initial track we had that we want to cluster. So using the method I described above, I'm going to look at 8 sets of forecasts. So I want to get a model that I can use throughout the storm. I don't want to be changing. I'm free to change every single forecast, but I want to get something that really gives me a sense of how the storm and the storm accuracy, storm forecast skill is evolving through time. So this is to look at the selection of optimal polynomial order. Now, the two things we have to determine are the Q, the polynomial order, and K, the number of clusters. Just from experience, from having done this, it turns out that it's more straightforward to select the order of the polynomial first, and then to go back and determine the number of clusters that makes sense. There's no requirement, but we feel that we've been getting a better solution that way. So what I've got here along the bottom is the number of clusters, and on the vertical axis is the measure for each of the individual metrics we're considering. So the BIC, which is based on the maximum log likelihood. This is MSD, it's the same thing. So that's the mean square displacement. So that's the compactness of the cluster, more compact when you're at lower values. And this is strength of cluster assignment. So the colors are the different polynomial orders. So black is linear, quadratic, cubic, quartic, and quintic. So going through and evaluating this, and the top row is for track, the bottom row is for a metric that my group designed for thinking about storm structure, and that metric's used by the National Hurricane Center. I don't have time to talk about it today, but it's something that we're very proud of. So looking just along the top row, it's clear that if I go from a linear to a quadratic polynomial, that my Bayesian information criterion values decrease. And again, they decrease further if I go to a cubic, and again with a quartic, and again with a quintic. And if I kept going, I would still get somewhat lower and lower. But the difference between the quartic and the quintic is much smaller than in the previous iterations. And again, if you look at the mean squared displacement, you can see, well, you can't see really a signal in the strength of the cluster assignment. And I think that is because we have a very strong cluster assignment. So this is really in noise. But so based on these analyses, we've decided that quartic, that fourth order polynomial, is the solution for this set of forecasts. We have a paper that's just coming out where we looked at 100 sets of storms, 100 storms, and tried to come up with an overall mega model, and you can get a decent one. You can do a reasonably good job, but this is only for 8 forecast times for one storm as an example. Okay, so we've decided we're going to use that quartic polynomial. Now we want to select the number of clusters. So what I have here is again number of clusters on the horizontal axis. These individual boxes are the individual forecast times that we're using going down, and then the means of them are along the bottom. So for say, just look at this box on the bottom left. You're testing for 2 through 7 clusters, and you're looking at the BIC, and here what we're plotting is the percent change as you go from, right, so you have 2 clusters. If you go from 2 to 3, you get a more compact solution that it changes by more than 5%. Again, you get another few percent change if you go from 3 to 4, another few percent change, right? So you're getting, say you're getting 4% change, now you're getting nearly 4% change, and then the gain, if you like, the improvement drops off rapidly after about 5. And if you look at the displacement, so the cluster compactness, the same thing, you're getting much greater improvements up to 5, and then the incremental improvement is much less beyond that. And again, the forecast strength of cluster assignment really isn't helpful. But so looking at these, we would say that 5 clusters is an optimal selection for number of clusters. And this is the bottom row you just saw. And then this is comparing it with what we would have said if we only looked at a 60-hour, so a 2.5-day forecast. And basically, I think that the evidence would still argue for that 5 cluster solution. So now we've taken cortex structures for 5 clusters. So this is our original set of ensemble members, and there is the 5 clusters that we've come up with using this method. So you can see a set of 3 that go out to sea, and there's another 3 here that are short, very fast and early landfall. And then in between, you have these others, the blue, cyan, green, and magenta. Okay, so it's 6 clusters. So these are the clusters. Black in there is the actual track. So these are the clusters that we're going to look at, and we're actually not going to look at the orange and the red because there's so few there. There's not much information to be added. So I want to quickly look at how the cluster evolutions differ. And I'm going to look at just the magenta, blue, cyan, and green clusters. We kept those colors consistently going from west to east with the centroid. So these are just the cluster centroids. All right, so I'll, till you tell me to stop, Anne, I'm just going to go along and show a couple of examples of why we think this is valuable. So this is, again, just to remind you of the centroids. So this is the furthest west, then towards the east, and the green cluster made landfall up in Canada, in far Canada. So, and here is what was observed from the satellite. So these are simulated satellite signatures for each cluster separately at the time the system was making landfall, compared to what the satellite image looked like at the time the system was making landfall. And so this is a different scale, unfortunately. But you can see that we had sort of an intense area of convection to the west, where the storm center is right on the coast. And we had a band of cloudiness off to the north, spreading out towards the east, southeast. You can see here, you've got that very intense area, perhaps a bit large, and then you've got this area that's less intense. So in this case, the cyan looks pretty good, but the storm is still offshore in that simulation. This one is a completely different physics. Another thing that we're used to looking at, ignore that second dot, is the radar composite. So again, this is the radar composite for the different systems. And if you look at the features of the radar here, I think you'd actually say that the blue cluster is the one that does the best job of reproducing the radar. So this is a tough ask because you're asking a model to put the right amounts of rainfall, the right amounts of moisture in the right places. And that relies on getting the physics of the convection, of the cloud activity accurate. That remains a big challenge, and that's one of the reasons that hurricane forecasting remains difficult, is that is having to produce faithful representations of the impacts of the convection. So
Jenny, we have about 5 minutes left. Anne delegated the time moderating to me. So if it's possible to wrap up relatively soon, that would be great.
Yep, that's great. I can show just one or two things and I'll wrap up. So, all right, this can be my second last show and tell, and then I'll just summarize. So what we're looking at here, again, these are those 4 clusters I talked about. And what we're looking at here, the reds and oranges are warm, moist air from the tropics, so the signature of tropical air. And the greens are cooler air masses. The white is showing you, if you were at 500 hectopascal, 500 millibars, where would the anomaly be at that level? So if you like, it's the pressure signature, but translated to height for a pressure surface. And so if it's a very tropical system, then that upper level is going to be very symmetric. So you can see the bullseye here in the cyan in the third panel from the left. And you're going to have a lot of warm air in the center, so that orange and red. And that's visible in both the cyan and green. These are the 2 clusters that stay out to sea much longer and are further away from land and are still well over the water at the time of landfall. The magenta has already just gone on land, and you can see that there's really not much left of the connection to the tropics. And the blue cluster still has a lot of tropical characteristics, but is starting to change away from that. And this is what the storm looked like at the time of landfall. And that's what's feature of an extratropical transition, which is one of my other major areas of research. A storm that forms in the tropics and lives to have a second life well outside of the tropics. And that usually means having dramatic impacts in terms of weather, but different to a tropical system. So this can be my last slide. So this is now thinking about intensity. The other one had similar information, which is why I moved on. So we're looking at the time of landfall, time going along the bottom, and the dots are when landfall occurred in the cluster compared to in the actual in the cluster itself. So when the cluster storm came ashore. And you can see in this case, again, the actual pressure value is similar. The minimum pressure that the storm in the model had is very similar but the time at which it reached that minimum differs, and it differs according to when the storm made landfall. And so again, the blue does a very good job of representing that. These are other indicators. So this is like looking at the symmetry of the cloud, showing that large values here indicate a more symmetric system. Okay. So that's a summary of that. I'll leave that and I'll just come to conclusions. So what we're wanting to do, taking an ensemble, a numerical model ensemble, is intended to span all of the possible solutions that could evolve from the current state as we understand it. Increasing amounts of data, the data deluge I call it, mean that this is going to be limitless. And if you provide a forecaster with 117 forecasts and say you've got an hour go, it's really hard for that person to synthesize all of that information. So what we're trying to do with this kind of a system is to take the wealth of information in the ensemble and synthesize it so that the information content isn't lost. Taking an average of the ensemble members would give you something that was in fact wrong. So that we come out with instead 6 scenarios that are that each have a physical synoptic basis. You can explain the physics, you can explain how the different systems interacted, what the environment did, and why blue is different from cyan, is different from orange or green or whatever. So that gives the forecaster then a tool that they can use to say, I'm an experienced forecaster. I know if I see this and this, then I can deduce that. So taking the clusters, you take that information, you make your judgment, and then you can go back to the cluster members and you can say, what's the distribution of the forecast rainfall? What's the distribution of possible intensities and so on? So you can drill down even a bit further. You're not just looking at landfall, at track. And I think what I'm just saying here is that what we showed was that when we applied this to Sandy, even just in this very brief summary I gave you, that we can learn something about how that system evolved specifically. So I'll leave it there. And this is a piece of work I did on hurricane sonification with my colleague, Mark Ballora, who we lost last year. So just for your amusement, I'll let that run in the background. And thank you very much.
Cool, thank you so much, Jenny. Yeah, if it's possible to mute the sound from there to see if you have any questions here. So if anybody has any questions, feel free to either use the raise hand button in Zoom, which you can find in the chat box, or you can also type your questions in the, you can find it in the parchment window, and or you can also type your questions on the chat box. And while we wait to see if there are any questions, I have actually a few. So let me actually start with one here at least, which is that I was curious about the way you account for time in those tracks when you do the clustering. Mm-hmm. So say, for example, that you have 2 models or 2 ensemble members that take exactly the same path, but they take it at different times. Like let's say that one of them is taking that path much more slowly and one of them goes much faster on that path. Would your clustering model be able to differentiate between those 2 cases?
Yes, it does. So in the partition we had for Hurricane Sandy, the 2 westernmost, the red cluster had only 3 members and they were very fast. And then the magenta cluster was almost the same trajectory, but slower. And so the clustering picked out the different forward speed, even though they were going along the same basic trajectory.
Cool.
Yeah. Oh, I see a question here. It's from Hayden. Do you want to take it directly?
Sure. I can't see.
Hayden, or I can read it.
Yeah, and maybe if you read the question.
So the question is, what type of terms, basically covariates, are usually entered into these models? The predictors.
What are the predictors? So yeah, we're really only using the track locations. There are two ways we did it. What I talked about today was purely using the tracks to develop the parameters for the models. We've also used the cyclone phase space, which is the other thing I sort of pointed at very briefly.
Yeah, I have a question too. So in ensemble, you use 117 members. So how do you define the ensemble? Is it the same dynamical model with different initial conditions or different models?
So it's defined loosely, yes and yes. Initially, we talked about ensembles. We had many models, and we said, well, why just choose one, right? You know, often people would have, this is my preferred model. I only look at the European model, or I only look at, you know, the GFDL model. And then we started realizing that we could, you know, trade off the deficiencies of the different models by learning from combining them. And so that was the multi-model ensemble. And then I talked about that there are different issues with individual models, each having their own issues, meant that the multi-model ensemble didn't necessarily give you the full range of uncertainty. You didn't really capture the full range of uncertainty using the multi-model ensemble. And so getting a single model and running it many times is also called an ensemble. So that we have many operational modeling centers that are doing that now. And then what I did is I took 4 of those. So the European Center, the US, the UK, and Canada, and combined those into a multi-model ensemble of single member ensembles, single model ensembles.
Let me follow up on that. So then when you generate these ensembles for a single model, how are they exactly generated? Like what are the sort of the variations that are introduced to the model? Because at the end of the day, it's sort of a deterministic model. So is it just the initial conditions, or are there also other types of variations?
Again, that depends. Yes, again, yes and yes. So initially it was just the initial conditions, and initially it was just trying to find the fastest growing perturbations in those initial conditions. So by perturbing the initial conditions to maximize the spread in the solutions. And so that was the initial approach. And then admitting the vagaries of the parameterizations for the convection and so on, then there started to be perturbations in how the individual parameterizations were implemented. So those both happened. But then more recently, as those things are developed, the perturbations that acknowledge deficiencies in the data or inaccuracies in the data or data quality or distribution are engineered, if you like, to capture the potential sensitivities in the system. So it doesn't matter if I put a pocket of dry air near the center of a hurricane, that's going to have a very big impact, right? Now, it may not have an impact I care about, but it may be very important if it's there near land. So the perturbations in the ensemble also capture information about the weather system as well as the model and the data.